We now explore the concept of energy in simple harmonic motion. Consider a horizontal spring initially stretched by amount x0 from its unstrained position and then allowed to contract to a final position xf. There is a force and a displacement, so the question is, what is the work done by the spring during this process? We know that, in general, the work is equal to Fs cosine theta, where theta is the angle between the force and the displacement. In this case, they are in the same direction, so theta equals 0 and cosine theta equals 1. The work then is equal to F times S. The magnitude of the restoring force of the spring is equal to K times X, which means that it is variable, and we have to take care to account for this. The displacement S equals x0 minus xf. Since the force is linearly proportional to the displacement x, we can account for the variable force by using its average value over the displacement range x0 minus xf. The average force over this range is given by F average equals 1/2 kx0 minus kxf. The work done by the elastic force of the spring is then given by F times S, which equals 1/2 kx0 minus kx final times x0 minus x final. Multiplying this out and rearranging, we have W elastic equals 1/2 kx0 squared minus 1/2 kx final squared, where the first term is the initial elastic potential energy and the second term is the final elastic potential energy. The elastic potential energy is the energy that a spring has by virtue of being stretched or compressed. For an ideal spring that has a spring constant K and is stretched by an amount x relative to its unstrained length, the elastic potential energy is 1/2 kx squared. We can now add elastic potential energy to the many other types of potential energies that can be used in problems that utilize the conservation of total mechanical energy. Consider, for instance, a mass hanging from a vertical spring. The spring has some unstrained length when the mass is not connected. If the spring is allowed to stretch slowly when the mass is connected, it assumes a new stationary equilibrium position, a distance h0 below the unstrained position. How do we find h0? We start by assuming the total mechanical energy before the stretch is equal to the total mechanical energy in the new equilibrium position. The only mechanical energies we need to consider are gravitational potential energy of the mass and the elastic potential energy of the spring. The total initial energy is mgh0 plus 1/2 k y0 squared, and this must be equal to mgh final plus 1/2 k y final squared. y0 is the initial stretch of the spring, which is 0. hf is the final height of the mass. We can define this as the zero of the gravitational potential energy, so we can set hf equal to 0. We are left with mgh0 equals 1/2 k y final squared. Y final is the final displacement of the spring, which also equals the displacement of the mass, h0. Therefore, mgh0 equals 1/2 k h0 squared. Solving for h0, we have for our final answer, h0 equals 2mg divided by k. In summary, we have found that the elastic potential energy of a spring of spring constant k displaced at distance x from its unstrained length is given by Pe elastic equals 1/2 kx squared. This new potential energy can be used to solve problems in which the total mechanical energy is conserved.